Hello everyone, this is my first lecture from the fourth module of fourth semester Complementary Mathematics course. Today we are going to discuss the topic orthogonal functions. First we can define the inner product. Suppose we are given two vectors, vector u equal to u1i plus u2j plus u3k, that is u1, u2, u3 are the components of the vector u, and vector v is v1i plus v2j plus v3k. Suppose u and v are two vectors in R3 or 3 space. Then the inner product or dot product. Inner product is also called dot product of u and v is a real number defined as the sum of product of their corresponding components. That is, it is denoted by this, or in some textbook it will be like this: u inner product uv. So inner product uv is nothing but u1 into v1 plus u2 into v2 plus u3 into v3. That is sum of the products of their corresponding components. That is the inner product or dot product of two vectors given in the component form. It also can be written as summation k from 1 to 3 uk vk. Now the inner product uv has the following properties. First one is inner product of u comma v is nothing but inner product of v comma u. That is the first property. The second property is inner product of k into u comma v, where k is a scalar, is equal to k into inner product of u comma v. That is, we can take k outside from this product. That is, inner product of ku comma v is equal to k into inner product of u comma v. Third one is inner product of u with itself is equal to 0 if u equal to 0, and it is greater than 0 if u not equal to 0. Inner product of u with itself is equal to 0 if u equal to 0, and it is greater than 0 if u not equal to 0. And the fourth property is inner product of u plus v comma w is the inner product of u and w plus inner product of v and w. That is the inner product of two vectors. Now we can define the inner product of two functions. Suppose we are given two functions f1 and f2 on the interval ab. So the inner product of these two functions on this interval ab is nothing but integral ab. It is denoted by this, and it is defined by integral a to b f1x f2x dx. That is, if f1 and f2 are two functions, then their inner product is actually this integral. Inner product on this interval is nothing but this integral a to b f1x f2x dx. This is the inner product of two functions. Now we can define orthogonal functions. Two functions f1 and f2 are said to be orthogonal on an interval ab if their inner product is equal to 0. So if the inner product of two functions f1 and f2 equal to 0, then we can say that they are orthogonal. That is, f1 and f2 are orthogonal on an interval ab if integral a to b f1x f2x dx equal to 0. Okay, this is the interval ab, so we have to integrate with from a to b, and if it is 0, then we can say that f1 and f2 are orthogonal. For example, show that the functions f1x equal to x square and f2x equal to x cube are orthogonal on the interval -1 comma 1. So we have to show that these two functions are in orthogonal with on the interval -1 comma 1. That is, we need to show that integral -1 to 1 f1x into f2x dx is equal to 0. That is what is we need to prove. So here the inner product, this is equal to integral -1 to 1 f1x into f2x dx, which is equal to, we have f1x equal to x square and f2x equal to x cube, that is x square into x cube dx. This is actually x power 5. So this is equal to, we can write directly this is equal to 0 because this function is an odd function, and the limit of this integrals are -1 to 1. So it will be 0. We have the properties of integral, properties of an odd and even functions. So this is equal to 0. Or if you're finding the integral, we get x power 6 divided by 6 from -1 to 1. So this is equal to 1 by 6 into x power 6 is 1 power 6 minus minus 1 power 6. This is equal to 0. Now we can discuss what is orthogonal set. A set of real valued functions phi naught, phi 1, phi 2, etc. is said to be orthogonal on an interval AB if the inner product of phi m comma phi n is equal to 0. That is integral a to b phi mx phi nx dx equal to 0 for m not equal to n. We know two functions f1 comma f2 are orthogonal if their inner product is equal to 0. That is the orthogonality of two functions. Now a set of functions is said to be orthogonal on an interval AB. If you are taking any two distinct functions from that set, then they are orthogonal. That is, if each pair of functions of that set is orthogonal. That is, inner product of phi m comma phi n is equal to 0 for m not equal to n. Now, orthonormal set. We discussed orthogonality of two functions, then orthogonality of a set of functions. Now, orthonormal set. When we can say that a set of functions is orthonormal. So, before that, we can discuss about norm of a vector or norm of a function. Suppose we have u is a vector, then the norm of u or the length of u is denoted by this norm u. This is called norm u or length of u, and it can be expressed in terms of the inner product. That is, norm square is equal to inner product of u with itself. Norm of u whole square is equal to inner product of u with itself. It is called square norm. So this is called a square norm, that is norm u whole square is equal to inner product of u with itself. This is called square norm, and the square root of that square norm is actually norm. Norm u is equal to square root of inner product of u with itself. So this is the norm of a vector or length of a vector. Now in a similar way, we can define the norm of a function. Suppose we have a function phi n, then the square norm of that function is square norm phi nx whole square is equal to inner product of phi n with the phi n itself. And norm of that function is nothing but, or length of that function is nothing but the square root of this square norm, that is phi nx is equal to this norm of phi nx is equal to square root of inner product of phi n with the phi n. In other words, we can say the square norm of that function is nothing but, square norm of a function is this is equal to inner product of phi n with phi n. We have inner product of phi n with phi n is equal to, on AB, we have this is integral from a to b phi n into phi n dx. That is, square norm is of phi n is nothing but phi n whole square is equal to integral a to b phi n square dx. And therefore, the norm is nothing but square root of this, that is square root of integral a to b phi n square dx. Now we can define the orthonormal set. Suppose we have a set of functions or an orthogonal set. Phi nx is an orthogonal set, that is phi naught, phi 1, phi 2, etc. We have this set phi nx, it is an orthogonal set. So an orthogonal set phi nx is said to be orthonormal if each of these functions has the length 1, or norm of each of these functions is equal to 1. That is, norm of phi naught is equal to 1 and norm of phi 1, phi 2, etc. are 1. So an orthogonal set is said to be orthonormal if each of these functions has length 1, or the norm of each of these functions is equal to 1. So for suppose, so we have a set phi nx is said to be orthonormal if each of these has length 1. Also phi m comma phi n, the inner product of phi m comma phi n is equal to 0 for m not equal to n. Now we can discuss an example. Show that the set 1 cos x, cos 2x, cos 3x, etc. is orthogonal on the interval minus pi to pi. So here we have the interval is minus pi to pi, and we have to show that this set is orthogonal. That means if you are taking any two functions from this set, then they are orthogonal. Okay. So for convenience, we let phi naught equal to 1. phi 1 equal to cos x, phi 2 equal to cos 2x, phi 3 equal to cos 3x. Generally, phi n is equal to cos nx. So here we have to show that this set is orthogonal. That is, we have to show that phi n comma phi m is, or the inner product of phi n comma phi m is equal to 0 for m not equal to n. So for convenience, we have taken this as 1 phi naught. So first we are going to prove the inner product of phi naught with the phi n is equal to 0. That is inner product of 1 with the cos x, 1 with the cos 2x, 1 with the cos 3x, etc. equal to 0. That is, we are going to prove first. So for n is equal to, n is not equal to 0, the inner product of phi naught with the phi n is equal to, we have minus integral minus pi to pi phi naught of x into phi nx dx. We have phi naught equal to 1, so 1 into cos nx dx. So integral of cos nx is nothing but sin nx divided by n. So minus pi to pi. So applying this limit 1 by n into sin n pi minus sin minus n pi. So we have sin minus n pi is equal to minus of sin n pi. So this is equal to 1 by n into sin n pi plus sin n pi. We have sin n pi equal to 0 because n is greater than 1, and that is n is equal to 1, 2, 3, etc. So sin n pi equal to 0. So this is 0 plus 0 divided by n, that is 0. That means phi naught is orthogonal with phi n. Phi naught is orthogonal with phi n for n not equal to, or for n equal to 1, 2, 3, etc. Next, we have to show that phi n is orthogonal with the phi m for n is not equal to m. So phi m comma phi n, the inner product of phi m with the phi n is equal to integral minus to pi phi m into phi n dx. We have phi m is nothing but cos mx and phi n is nothing but cos nx. So integral minus pi to pi cos mx into cos nx dx. We have, by trigonometric identity, we have cos b is equal to cos a plus b plus cos a minus b divided by 2, because we have cos a plus b is equal to cos a cos b minus sin a sin b, and cos a minus b is equal to cos a cos b plus sin a sin b. So adding cos a plus b and cos a minus b, we get 2 into cos a cos b. So cos a cos b is equal to cos a plus b plus cos a minus b divided by 2. So here we have taken a equal to mx and b equal to nx. So cos a plus b is cos mx plus cos nx, and cos a minus b is cos mx minus cos mx minus nx. The integral of cos m plus nx is sin m plus nx divided by m plus n, and integral of cos m minus nx is equal to sin m minus nx divided by m minus n. So applying this limit, we get 1 by 2 into sin m plus n into pi minus sin m plus n into minus pi, that is here plus pi, divided by 2. This is first one, divided by m plus n. So this is equal to 0 and this is equal to 0 because m and n are positive integers. So this is equal to 0 and this is equal to 0. Similarly, we'll get here are 0 minus 0 divided by m minus n for this also. So 0, and so the value is 0. That is phi m comma phi m. That is, the inner product of phi m with the phi n is equal to 0 for m not equal to 0. Therefore, phi m comma phi n are orthogonal where m not equal to n. Therefore, we have shown that the set 1 comma cos x comma cos 2x etc. is orthogonal in the interval minus pi pi. Next, another example, find the norms of each function in the orthogonal set given in the previous example. So we have to, we actually, we proved that this set is orthogonal. Now we can, in the next example, we need to find the norms of each of these functions. So first we have to find the norm of this, and then we have to find norm of cos x, cos 2x, etc. So we already suppose that phi naught equal to 1 and phi m is equal to cos mx, right? So for phi naught equal to 1, we have the square norm phi naught of x whole square is equal to minus integral minus pi to pi. You know, this square norm is actually the inner product of phi naught with the phi naught. That is integral minus pi to pi phi naught of x into phi naught of x, or phi naught of x whole square dx. phi naught of x is equal to 1, so 1 into 1 dx, that is integrating this we get x from minus pi to pi, that is pi minus minus pi, that is 2 pi. So the square norm of this phi naught of x is equal to 1 is 2 pi. Therefore, norm is nothing but square root of 2 pi, that is norm of phi naught, that is norm of 1 on the interval minus pi. Here the interval is minus pi to pi. Norm of 1 in the interval minus pi to pi is equal to square root of 2 pi. Now, next we have the functions cos x, cos 2x, cos 3x, etc. So for n is equal to 1, 2, 3, etc. we have phi n is equal to cos nx. Now finding the norm of that function, the square norm is nothing but we have integral minus pi to pi, or this is equal to phi n comma phi n. The inner product of phi n with the phi n, that is integral minus pi to pi cos nx into cos nx dx, that is cos square nx dx. We have cos square nx is nothing but 1 plus, we have cos square x is equal to 1 plus cos 2x divided by 2, so replacing that we get cos square nx is equal to 1 plus cos 2nx divided by 2. So this is equal to integrating this we get, here we get 1 by 2 into, on integration we get x plus integral of cos 2nx is sin 2nx divided by 2n from minus pi to pi. So this is equal to 1 by 2 into pi minus minus pi plus sin 2n pi, this is 2nx, sin 2n pi minus sin 2n pi. So plus 2n pi divided by 2n. So this is 0 and this is 0. So we get 2 pi by 2, that is pi. This is equal to pi. So square norm is equal to pi. Therefore, the norm is equal to square root of that pi, that is root pi. Now, suppose we have an orthogonal set of non-zero functions phi n x. Now we can normalize this set. Normalizing means we can convert this set to an orthonormal set. That is by dividing each function by its norm. Suppose we have this function, this set of functions phi nx for n equals 0, 1, 2, 3, etc. That means suppose we have phi naught, phi 1, phi 2, etc. Let this set be orthogonal set. Orthogonal set. Now we can normalize this set to get corresponding orthonormal set by dividing each function by its norm. That is, if this set is orthogonal, then phi naught divided by phi naught, norm of phi naught, phi 1 divided by norm of phi 1, phi 2 divided by norm of phi 2, etc. This set will be orthonormal. That is, an orthogonal set can be normalized or made orthonormal by dividing each of the functions by its norm. Okay, so if this is orthogonal, then this set is orthonormal. For example, we obtained that in the previous example we have the set phi naught is 1, phi 1 is cos x, phi 2 is cos 2x, phi 3 is cos 3x, etc. We proved that this set is orthogonal. The set is orthogonal. Now, dividing each of these functions with its norm, with the corresponding norm, we get an orthonormal set. We obtain that the norm of 1 is square root of 2 pi. So 1 by square root of 2 pi here. Norm of cos nx is equal to square root of pi. So dividing each of these functions with their norm, that is cos x by root pi, cos 2x by root pi, cos 3x by root pi. So this set is orthonormal now. Clear, this set is orthonormal because we obtained that 1 cos x, cos 2x, cos 3x. This set is orthogonal. So we divided each of these functions by their corresponding norm. So this set will be orthonormal now. Now we have orthogonal set or weight function. That is, we studied that two functions f1 comma f2 are orthogonal if orthogonal on an interval ab if integral a to b f1 into f2 dx is equal to 0 or their inner product is equal to 0. Now we can say that these two functions are orthogonal with respect to a weight function. With respect to a weight function w, if their inner product with respect to this, that is w f1 f2 dx equal to 0. That is, The set phi naught, phi 1, phi 2, etc. is said to be orthogonal with respect to a weight function W. With respect to a weight function W on an interval AB, if integral A to B W of x into phi mx into phi nx dx equal to 0 for m not equal to n.